right, so let's get started. Any questions or anything before we get going today? So of course, happy Halloween. Hopefully lecture won't be too scary today. And then don't forget, registration has begun. So make sure you register for classes. Are people planning on taking CHEM 105? Just kind of curious. I don't really expect people to, since usually if you're just going for like a general science credit, you just want the one series. And taking the entire year doesn't really help you for 220, the 200 series. I mean, it's only 104 helps. But I was just curious since it's being offered online, but I would like to do more with it. But so register. And I know some classes are offering bonus points for registration, but I don't know how y'all feel about that. Just because I don't know who's like transferring, not transferring. I just want to provide kind of equal opportunity. But I'm also happy to provide bonus points as well. This is incentive. Thoughts, feedback?
To register for chemistry classes or just
any classes? Just like if you register, you know, before the quarter ends, then I'll give bonus points. But
heck yeah, yeah, I like that.
yeah, it's just there's actually like apparently because all the professors were like discussing this idea, and apparently there's like a lawsuit though at University of Oregon because I guess it wasn't fair because somebody was transferring. So I didn't want to like open up a can of worms, but I'm more than happy to do bonus points if everybody's happy with it. And if you are transferring, you can always write me a letter like I'm transferring to here, and that'll be your bonus point. All right, I just don't want to get sued. So let's do that. We'll do bonus points. Everybody likes bonus points. So bonus points for registering. We'll do before December 2nd, or 1st. What's the last day of the quarter? I think it's the 2nd. So just send me an email or something that says, hey, I registered. And then if you're transferring, just write me a letter or something. What your plans are, or if you're graduating, you can just tell me I'm graduating and I'll give you bonus points. So just have some plan and everyone can get bonus points, equal opportunity. All right. So the game plan for today is we're going to go over oxidation reduction reactions. Again, just a bit more in detail. So last week we just kind of briefly went over it, saw the types of reactions that tend to be oxidation reduction. But then we'll look into that. And then we'll start with chapter 6, which is energy. So we'll see how far we get today. And so kind of thinking back to our examples of types of reactions, so we had said at least some evidence of oxidation reduction reactions is when you have something in their elemental form and then it goes to a compound or vice versa. But now we're really going to learn, well, what does it truly mean? And so anytime we have these oxidation reduction reactions, or redox, so commonly you see this term, redox reactions. And all that is saying when you have an oxidation reduction or redox reaction is that the electrons are transferred from one reactant to another. And so many times they involve the reaction of a substance with oxygen. And so if we look at this case, let's break it down. So do we remember what the oxidation state is if it's an elemental form? 0. So 0. And then oxygen, what's this oxidation state? So 0 again, so both in their elemental form. And then, so now we make some sort of iron oxide. So what's our oxidation state on this iron now? always reverse swap trick, see if that works. Well, the 2 goes back. Yeah, so that means that the iron's 3 plus, oxygen's -2, which that checks out with our periodic table, so we don't need to multiply it by any factor. And so now we're seeing where the electrons are being transferred to. So in this case, if we went from iron 0 to iron 3, so we were at 0, now we're +3. Are we gaining or losing electrons? So losing. And then now we want to also practice kind of bookkeeping. So each iron itself is losing 3 electrons, but then we have 3 times 4 from our balanced equation. So this is 12 electrons total here in this transfer. And so the electrons also have to be balanced. And so now our other case, so we're going from oxygen of 0 to -2. And so this one was losing, so that must mean that the oxygen is gaining electrons. And so each one is gaining -2. So -2 times 2 gives me -4, times this 3 gives me 12 electrons as well, so gaining 12 electrons. And so again, really important that we're losing and gaining the same amount of electrons. So let's look at this combustion reaction. So combustion reactions, these tend to be a little funny with their oxidation states. And so this is 0. But now how might you approach this? And so kind of the why we're about to get some weird numbers is to really get the oxidation state of an organic compound, we'd have to draw out the structure. But in this case, we're not given that, so we can just kind of get our average then value. And so base it off of your hydrogen. So you know your hydrogen's going to be 1 plus. There's 18 of them, so what must the charge or oxidation state of that carbon be? And it may not be a whole number. So take a minute or two. So I don't think 9 quite gets you there. So remember, you're trying to make the whole thing 0. So we have like 0 is equal to, so 18 times 1 plus 8 times x. You could also do the reverse swap trick. You just kind of have to do a little factor. So if we do reverse swap trick, so you have 18 plus and 8 plus, or sorry, this has to be negative. So this is going to be 18 negative. Now, of course, 8 plus is ridiculous, right, for the oxidation state of hydrogen. But we can just multiply it by our factor. So if we multiply everything by an 8, that gives us hydrogen to 1 plus. And I didn't fire up my calculator. And so then 18 divided by 8 is 2.25. Then it has to be negative, since again we're assigning a +1 charge to hydrogen. So negative 2.25. You would have gotten that same thing algebraically. So move the 18 over. So then you have negative 18 is equal to 8x. And then solve for x. So same thing, negative 18 divided by 8 to give you that negative 2.25. And so again, this is just more of a formal number. And so we do our reaction. So oxygen goes to the -2 oxidation state. And if oxygen is -2, what is carbon? +2, or remember there's 2 of them. So +4. And so now we want to do some electronic bookkeeping. So this one gets a little messy. Now we have carbon going from -2.25 to +4. So that's losing electrons. And let's see how many. So if you wanted to calculate it, so 4 minus 2.25. So that's per atom. Then there's 16 of them, so times 16. So that's 100 electrons being transferred from here to here. So 100 electrons lost. Now, does that accounting work out for oxygen? So let's see. So oxygen, each one of those is changing from 0 to -2. So -2 per oxygen, or 2 electrons gained, I mean. And then so 2 times 2 is 4 times 25. That gives us 100 gained on our oxygen. So it does indeed work out. Let me write that better. So 100 electrons gained. So each oxygen goes from 0 to -2 times 50 of them gets us 100. And then so our last one, so again, this was our little demo that we did. So hydrogen gas plus oxygen gas forms water. And so they both start out in the 0 oxidation state. And then what's the oxidation state of hydrogen and water now? So what's hydrogen usually from our periodic table? So 1, and then what's oxygen? 2 or -2. And so there we have it again. So 0 to 1, losing electrons. So hydrogen is losing electrons. And so each one is losing 1. 1 times 4, so it looks like 4 total. And so same thing with our oxygen. So now it should be gaining 4. So oxygen goes from 0 to -4, or excuse me, -2. So -2 times 2 gives me 4 electrons. So any questions about this kind of so far? Yeah.
Like a clarification, so it's one group of elements will lose oxidation states, and then others that has to gain it in the same amount.
Yeah. So just one is gaining electrons, the other is losing the same amount of electrons. So that was our demo that we did. And so now let's introduce some new terms. And so this is their hint, and that's why I was saying anytime you see something in its elemental form being lost or gained, or making something in its elemental form, then you're probably doing a redox. So to convert an element into an ion, the atoms must gain or lose electrons, or again, vice versa. And so atoms that lose electrons are being oxidized. So if you say something's oxidized, they've lost electrons. Atoms that gain electrons are called reduced. So gaining electrons, reduced. So if we look at this case, and so just start by writing your oxidation states again. So what's my oxidation state for sodium here? Chlorine. And then sodium. And chloride. So -1. And so now there we have it again. So sodium goes from 0 to 1 plus. And so it's losing electrons. So we can say that sodium is undergoing oxidation, or it was oxidized. And it's generally the metals. So you'll notice metals tend to be oxidized, right? They want to lose electrons. We've seen that. So metals are usually oxidized. So metals provide the electrons for the most part, so they're oxidized. So we see that over and over again. So sodium, potassium, they're also known as good reducing agents because, again, those metals giving up those electrons. And then so we can say chlorine then is reduced or underwent reduction. And so again, it gained those electrons going from 0 to -1, so it became more negative, gaining electrons. And so there's nice little pneumatics to help you remember. So I have 2, so you can pick your favorite. So I'm originally from Texas, and so oil's big out there. So we have oil rig as one of them. And so that stands for, let me make some more space. So oxidation is losing electrons. Reduction is gaining. So that's one mnemonic. And it's maybe you don't like oil, or you want something cuter to remember it by. And so the other one that I know is Leo goes grr, and Leo can be your favorite cat species. So lion, tiger, leopard, whatever Leo is. So Leo goes grr, and this means losing electrons is oxidation, and gaining electrons is reduction. So they both say the same thing, so either one, you can pick which one you like, write it on your test, write it on your periodic table. So you always remember either oil rig or Leo. The lion goes grr. And so like we've been practicing to identify the redox reaction most properly, you have to, of course, assign its oxidation states and then see who is increasing in oxidation state. So it's becoming more positive, so oxidation is losing, so that means we're losing electrons. Then reduction, you see a decrease in oxidation state, again, as it becomes more negative, gaining those electrons. So we see the sulfur is reduced from 0 to -2, so again, formally decreasing its oxidation states. And so we say carbon was oxidized since it lost electrons, and sulfur was reduced from gaining electrons. So if we wanted to revisit these examples, so let's look in the iron oxide formation. So is iron being reduced or oxidized? So oxidized, so we said oxidation is losing. So it went from 0 to 3, so it is losing. So oxidized, iron oxidized. What about in the second one? So who underwent oxidation? So carbon went from -2 to +4. So oxidation is losing, so that means carbon lost those electrons. And then in this last one, so who was oxidized? So hydrogen. And so in all these cases, oxygen is being reduced, so oxygen became more negative. And we'll introduce another term, but oxygen is also known as the oxidizing agent. And if it's the oxidizing agent, it's the one that is being reduced. And so that means all of these, so the iron, the carbon, the hydrogen, are all called reducing agents. So they are supplying the electrons, so they will force the other element to reduce. And so that makes sense for oxygen. So you often hear, right, oxygen is an oxidizer, so it adds oxygen to things. So that is another kind of sign of an oxidation reduction reaction, is adding oxygen to something. It's just not an all-inclusive definition. Blah, blah, blah. So we've kind of gone over this, so this is just a recap of the rules which we've been practicing. So again, most important rule number 1 that we've seen. So free elements always have the oxidation state of 0. So just star it, mark it, remember it. And so this we've already kind of seen. This is just repeated. So we're following what they tend to do. And of course, the sum of all oxidation states has to be 0. So again, we've been practicing that. Nothing too crazy there. And so other oddities. So when we are dealing with our polyatomic ions, so the sum of the oxidation states of all of the atoms in a polyatomic must equal the charge. And so in this example here, so let's say you're given nitrate, trying to figure out the oxidation states. Well, oxygen is always one of your safe ones. So if we know oxygen is -2, that means we can figure out our nitrogen. So they set up the algebra here. So just our overall charge is -1. Then we have 3 oxygens times -2, and then plus some factor of x. And so then we can solve that x equals 5 for our oxidation state for nitrogen. And so how we determine things. So again, this is kind of our cheat sheet, what we base it off of. So we always expect fluorine to be in the -1 oxidation state. So we can base off of our metal oxidation states off of fluorine. So same thing, hydrogen is always +1 unless it's a metal hydride. And we don't see too many metal hydrides, but like aluminum trihydride would be one, or boron trihydride. You could also have some sort of like iron hydride compound. And in those cases, H is -1. But again, only if you see hydride, that's going to be your hint. So hydride refers to the -1, but again, any other time you see hydrogen, it's always +1, +1, +1. And oxygen's always -2, unless it's in peroxide. So anytime you see a peroxide, though, that's your hint, things are different. And peroxide 1 O2 unit is equal to -2. And so that means oxygen would have a -1 charge for a peroxide. So for example, the hydrogen peroxide that you're familiar with is H2O2. And so this has a -2 charge that balances with those two hydrogens. And so again, that's just a peroxide case where you have an exception. Otherwise, oxygen is always -2 like we've been seeing. And then of course our patterns like we've seen, so we know our halogens are generally -1. We may see some exceptions with purely covalent compounds of halogens, but otherwise they're always -1. Group 6, we've seen they follow just like oxygen, or at least they tend to, unless there's something odd going on. And so group 5, right, they tend to be -3, unlike we just saw for nitrogen in here, so that was +5. And again, that being in a covalent compound makes them a little trickier. And so just, again, recapping what's going on. And so you guys are asking the right questions. And so like you've realized, they have to occur simultaneously. So one is gaining, the other one's losing. So somebody has to be supplying the electrons, and somebody is taking them. So there are the terms that we introduced. So the reactant that reduces an element in another reactant is called the reducing agent. And so the reducing agent is oxidized. So reducing agent supplying the electrons. Again, the common examples, sodium, potassium, those are really strong reductants, of course, but they're very helpful in metal chemistry, and you can also make little compounds to kind of, what I would say, make it a gentler reaction. So this is more of an aside, but for example, you can make sodium amalgam, and so the amalgam is with mercury. If I remember correctly, it's about 5% by mass. And so all you do is you pop a little mercury in with your sodium. It helps clean it. It makes a little poo. And then it just intercalates the sodium among the mercury. So then when your little compound goes and sees it, it doesn't just get hit with a huge equivalent of sodium, but rather it's reacted more slowly with the mercury. And so same thing with potassium. So there's something you can make called KC8. And all this is you like heat the crap out of potassium and carbon, and it makes a really pretty gold powder that is also a really nice reducing agent.
I was a Navy SEAL for 18 and a half years. I was medically retired from PTSD. Had I not found psilocybin therapy, I wouldn't be alive.
Veterans like Chad deserve to heal. Protect their right. Vote no on 15203.
This video has been sponsored by NordVPN. You can get a special deal and support the channel by visiting nordvpn.com/NileRed.
So some people have told me they're a fan of Niles Red.
Over the years, I've worked with mercury many times, and it's almost always a bit of a pain because it requires special handling evenly throughout the mercury. The reason for this was because as the sodium combined a small amount of mercury piece, I immediately dropped it back into the toluene. In this shot, I only showed me cutting one of these really small pieces, but I ended up cutting most of the sodium down to around this size. Now it was time to set up the mercury side of things. As I mentioned before, this reaction was apparently notorious for a lot of splashing, as well as flaming sodium. To deal with this, some procedures suggested just using a really large flask, but they were also doing it on a much larger scale. I figured that because I was only doing this with a few milliliters of mercury,
So my one criticism of this procedure is I would not have put the mercury in first. So the way I've always done it is you always put your metal in first, but it won't make too much of a difference. But you'll see he has some difficulty. once he
a
actually-
large test tube would probably be fine. So I poured in a random small amount of mercury, and then I pulled out my small piece of sodium, quickly dried it, and threw it in. I was kind of nervous that I'd immediately get fire in molten sodium, but nothing happened. The major reason for this seemed to be that the sodium was just a bit too tarnished, and it prevented it from coming into contact with the mercury. The sodium's also way less dense than the mercury, so it kind of just floated on top, which didn't really
Yeah, I've never had this problem before, by the way, if you add it the other way.
help either. To fix this, according to some procedures that I read, it's pretty common to use something like a glass rod and to shove the sodium into the mercury. Then once it's underneath, it can be scraped and crushed to expose the fresh sodium. So I decided to try this, and initially I still had some trouble getting it started, but then suddenly there was a little thump and all the sodium instantly disappeared. Then when I mixed it around a bit, I noticed that the texture of the mercury had also changed. The reason for this was because as the sodium combined with the mercury, it didn't do it uniformly. The reaction was extremely fast, and the mercury that was around the sodium took up most of it and got a relatively high concentration. And when the concentration of sodium gets above about 1% by mass in mercury, it starts to solidify. So what this gave me was a bunch of solid sodium amalgam mixed in with some regular liquid mercury. However, after I let it sit there for a few minutes, the sodium slowly dispersed evenly throughout the mercury and most of the solid bits disappeared. It kind of went back to more or less looking like regular mercury, but the one major difference was that it was now sticking to the glass a bit.
All right, so that's just how to make your sodium amalgam with mercury. And it was hard to see in that video, but again, there should be like a little poof as it reacts. And why we like to put it in the amalgam is the amalgam helps clean it. So you saw he was like complaining that the sodium was oxidizing really readily, but the amalgam will clean that all up. So that's how you would prepare a nice reducing agent if you wanted to do some sensitive chemistry. And so then a reactant that oxidizes an element in another reactant is called the oxidizing agent. So again, we saw that usually oxygen is an oxidizing agent, but obviously there are other ones. And so we saw in this case, our chlorine went from 0 to -1, so it was reduced, meaning it's the oxidizing agent, so it's the one taking in those electrons. All right, any other questions about oxidation, reduction before we shift gears? All right, let's start chapter 6 then. So chapter 6 is energy now. So energy, work, and heat. And so let's define energy. So energy is anything that has the capacity to do work. So of course, work is a force acting over a distance. So like pushing this podium would be doing work. And so energy can also be exchanged, of course. So we can have like potential kinetic energy. So I'm holding this pen at this certain position. So of course gravity is working upon it and I'm doing work. So if I let go, now that potential energy is transferred to kinetic. And then we can measure heat as the flow of energy caused by a difference in temperature. And we'll relate this to exothermic and endothermic reactions. So exothermic are reactions that feel hot. Endothermic feel cold. So that's telling us which way heat's being transferred. And so heat and work are just the two different ways that an object can exchange heat. And so we see that a lot with chemical reactions, that things either heat up or feel cold to us. So exothermic, maybe y'all are getting out those little hand warmers. So a lot of them are just little iron powder, and then you break it up, expose it to the air, and the iron starts reacting with the oxygen, and that's an exothermic reaction, so it heats up. Endothermic, if I remember correctly, I believe ammonium chloride is an endothermic reaction when it's dissolved, so you break up your little instant cold pack, so it's ammonium chloride salts, and then I believe it's just water on the other side, and then that dissolving requires energy, so your body is supplying the energy for that ammonium chloride to dissolve, giving you that nice cold pack. So now looking at different types of energy. So kinetic energy is the energy of motion, so something in motion. This can also be electron movement. So that's kinetic energy, your current, things running, moving. And so thermal energy is energy associated with temperature. Then potential energy is energy either stored in an object due to its position or its energy associated with the composition. And so this is, of course, the flavor we're going to be looking at. So eventually thinking of bond making and breaking. You can also relate this to food. So your food has energy associated with the composition of it. And of course, your body makes it, processes it, and then you get all that energy back. And so we saw our gravitational potential energy. Again, it just goes from one form to the other. So in this side, it's all fully potential energy, no kinetic energy. Then as we release it, it gets transferred from potential to kinetic energy. And so we said electrical, that was kinetic. And then heat or thermal energy. So this is also going to be associated with molecular motion. So of course, if you increase the thermal energy, we've seen this with our state changes, or at least our preview into state changes. So we do state changes by adding more energy, and then those molecules start moving faster, faster, faster. And then, so light energy is, again, also kinetic or radiant energy. So that's related to your energy transitions. And nuclear, that would be considered potential energy. So that's what's stored in our structure in the nucleus of the atom, so changing it. And then, of course, chemical, that's also potential energy. And again, that's what we'll be looking into. So related to the structure of the atoms and how they're attached. So now let's look at our units. And so you may be familiar with this formula. So kinetic energy is 1/2 mv squared. So this is just maybe something you've seen in physics before, but why we care about it is because we need to get our units. So we have mass is in kilograms, and then V is just velocity, so that's meters per second squared. So then kilogram meter squared over second squared. And so this is known as a joule. So anytime you see joule, this is all it is, kilogram meter squared over second squared. And this is also equivalent to 1 Newton meter. I would highlight this part. So when you're doing your dimensional analysis, if you get this thing, know it's a joule, and a joule is this. And so a joule is, of course, also just defined as the amount of energy needed to move 1 kilogram mass at a speed of 1 meter per second. And so you may be familiar with calories. However, the food calorie you're familiar with is actually big cal. And so let's look at what a true calorie is. So a calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And so that means a kcal would be the energy needed to raise 1,000 grams of water. And so anytime now you see that food calorie on the back of your label, know that it's really 1,000 of these little calories. Now you can calculate all that energy you're getting. And so other units, so really the most relevant one is going to be calories in joules. So if it comes up, so 1 calorie is 4.184 joules. And then, of course, you can remember the kilocalorie is 1,000 calories, and a food calorie is 1 kcal, or 1,000 calories. And then you also have this conversion. It just doesn't come up as much in our calculations, but maybe you've heard kilowatt hour when they talk about energy, and so now you can understand that that's 3.6 times 10 to the 6 joules, so a lot of energy. I've only watched it like once, so I don't remember what the critical power was. And so now let's look at the first law of thermodynamics. And so this is conservation of energy. And so the first law of thermodynamics means that the total amount of energy in the universe is constant. So it is conserved. So you can never design a system that will continue to produce energy without some source of energy. So have you heard of those like perpetual motion machines, or in theory? So it's just a theory of could you ever make a machine that just self-powers itself, but of course that violates the first law of thermodynamics. Let's just pull up the Wikipedia. So this is just a perpetual motion machine. And so again, this is a theoretical, a hypothetical machine that could do work infinitely without an external energy source. But as we're learning, this would be impossible. So now let's look at the details. And so chemical reactions involve breaking bonds in reactant molecules and making new bonds to create the products. And so therefore we can figure out, and this is the heat of formation of the reaction. So basically, is it exothermic? Is it endothermic? Will it feel hot? Will it feel cold? So we can estimate this by comparing the cost of breaking old bonds to the income from making new bonds. So it's favorable. So when two things make a bond, that's really energetically favorable. So you have orbital overlap, and that causes the energy to drop. So that's where you get kind of the income from making a new bond. And of course, breaking bonds, it makes sense that we have to put energy into breaking a bond. So they're quite happy. They're sharing electrons, so we have to put energy in to break them apart. And so the amount of energy it takes to break 1 mole of a bond in a compound is called the bond energy. And so this is calculated in the gas state. And the other thing is it's homolytic. And most bonds are homolytic. And so let's see what we mean by homolytic. This is a quick aside. So homolytic just means a bond cleaves evenly. So let's just take methane. instance. So if you do a homolytic cleavage, let's just kind of zoom in on one bond here. Now we're just looking at the CH bond. And so if you do a homolytic cleavage, well, I can't draw half arrows apparently. So your textbook should have like a little half arrow. So half arrows indicate movement of one electron. So anytime you see that, it's just one electron moving. And so we would break it, return that one electron to carbon, return the other one to hydrogen. And so that's how most bonds form, right? That's how we've been doing it with kind of our Lewis dot structures that we've been practicing. But I just wanted to point out one example of a heterolytic bond. So heterolytic bond. And so one of the few examples of this would be this borane nitrogen compound. So it's drawn like this. But if we do some quick Lewis dot structures, so BF3 should look like this. So boron, we know only has 3 valence electrons. So one goes into each of those bonds. Fluorine, of course, also brings one to the bond. So there's our BF3. And then what do we know about ammonia? How many lone pairs does ammonia have? So lone pairs. So one lone pair. And so now looking at this, the only way for them to come together is the nitrogen is donating both of those electrons in that bond. And so sometimes you might see it more accurately drawn like this. So if you have this kind of arrow notation, which isn't commonly used, but this is just to show that nitrogen contributes both of the electrons. And so anytime you see that, this is meaning whatever this compound is, so it could be phosphorus, could be a metal if you're looking at some sort of metal compounds. But that's just saying it's putting in all the electrons. And so if you were to do a cleavage on this, it would be called heterolytic, since formally the electrons would return back to the nitrogen, giving us our BF3 and ammonia. All right, so that was just a quick aside. So again, most bonds are homolytic, but there's one of your few heterolytic cases. All right, so back to where we were. And of course, the actual bond energy depends on surrounding atoms and other factors. But again, we have our average bond energies that can be used to estimate our delta H of our reaction. And of course, if the bond energies were found in the gas state, then it works best when you're talking about reactants and products in a gas state. And so bond breaking is endothermic. And so it's endothermic means you have to put energy in. So that's a formally positive value. So again, putting energy into the system. And then bond making is exothermic. So that's favorable again. Energetically, they want to be in bonds. And so that gives you a negative value, so getting energy back out. And so then we can find our delta H of our reaction by summing the total number of our bonds broken plus our total number of bonds formed. And of course, this should be something negative, and then we'll get our answer. And so we covered single, double, triple bonds, and so now we can kind of appreciate the trends. So of course, the more electrons two atoms share, the stronger the covalent bond. That makes sense. And so you can just see that reflected in their relative bond strength. So a carbon-carbon single bond is 347 kilojoules compared to a triple bond that's 837. So same thing, carbon-nitrogen, so this is almost 900 kilojoules, while a single carbon-nitrogen bond is 305. And so the other kind of trend is the shorter the covalent bond, the stronger the bond. And so in this case, if you have a bromine-fluorine bond that has a radius or a bond strength of 237 kilojoules, so nice and short. So thinking about the radius of fluorine, right? Fluorine has a smaller radius, so it's just physically closer. While the bromine, so again, they're just larger and slightly weaker, so 193 kilojoules. And so it makes sense that bonds get weaker down a column, but then they get stronger across the period. So as you go closer to getting those electrons filled up, so again, thinking of your electronegativity value trend.
And are those all covalent?
Yeah, so this would be for covalent bonds only. So this, when you're looking at this chart, the average bond energies, so yes, this is for covalent compounds. And so on an exam or something, you'd either be provided this chart or I would give you, the bond energies that you need or blah, 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 and then figure out the delta H of the reaction. So let's do that. Let's practice this one. So we're looking at this reaction of methane. Oh, actually, let's do this one. My apologies. Let's start with this example that they showed us here. So we're trying to figure out, well, what's the enthalpy of this reaction? And so we have, let's write out our reaction. So methane plus chlorine gas gives us chloroform. So just replacing one of those carbon hydrogens with a chlorine bond, so chloroform, plus making an equivalent of HCl. And so first thing, just make sure it's balanced. And then, so the other thing you might want to do when approaching these is you might want to just draw out the structure so you can count how many bonds and if they're double, single, or triple. So we can clearly see, okay, we have 4 CH bonds, they're just single. Then chlorine, so we know they just make 1 bond between them for the diatomic. So of course it was oxygen, right? We'd have to take into account the double bond, nitrogen, a triple. And then draw out our products. So we just replaced one of those carbon-hydrogen bonds with a carbon-chlorine bond. And then we also made HCl, so swapping out a chlorine-chlorine bond for a hydrogen-chlorine bond. And so now this just walks us through the steps that we have to do. So first we have to put in some amount of energy to break the bonds. So we have to identify, well, which bonds are we even breaking? And so we probably want to break 1 CH bond so we can make a carbon-chlorine bond later. And we need to break the chlorine-chlorine bond to make HCl. And so now we want to reference our chart now. So again, this is delta H in. And you can set up your bookkeeping. So I like to make 2 columns, so bonds broken versus bonds formed. And so now we just have to get the numbers from the chart. So 1 carbon hydrogen bond and 1 chlorine chlorine. And so now I'm going to scroll up. Oh, just so you're aware. So if you see CO2, you want to use this value for the carbon oxygen bond. So it's a little stronger in CO2, so it's 799. Let's go back. So now I'm trying to find, there's carbon hydrogen. So carbon hydrogen, 1 bond is 414. So that's the energy we have to put in. And that's kilojoules per mole. So 1 mole of it. And then chlorine, chlorine. So where is that on the chart? 243. Oh, there it is. I'm blind. So 243. So now just add those up to see how much we have to put in. So 414 plus 243. So that's 657 kilojoules in the system. So put a plus sign here to remind you, right? It's going in, it's endothermic, you're supplying energy. So now let's see how much we get out. So now we're calculating our new bonds formed. So we made a new carbon chlorine bond and a new hydrogen chlorine bond. Let's see, so what's my carbon chlorine bond worth? Oh, there it is. So carbon chlorine is 339. And then HCl, 431. So now add those up. So 339 plus 431. And so now this is energy that we gain back, so it's negative. So do we all get negative 770? And so the last bit, so delta H then is equal to 657 plus our bonds formed, so plus our negative 770. So this gives us the heat of formation for our reaction. So negative 770 plus 657. So I get negative 113. And that would be kilojoules for this reaction. And so that's telling us this reaction would be exothermic. So heat would be released. It would feel hot to us. So see if you can try this one. So I'm going to let you write down the equation, and then I'll scroll back up so you have the numbers. But again, you might want to write out like each molecule to help you, so you keep track. So we have 1 equivalent of methane, so CH4 plus 2 equivalents of water gives us 4 equivalents of hydrogen and 1 equivalent of CO2. And don't forget, for that CO2, you use the special value of 799 for those bonds, for 1 CO bond. Now I'll scroll up here. Was it should already be balanced. I'm just double checking. So 8 hydrogens, 8, 1 carbon, 2 oxygens. But yeah, you would want to balance it before you begin. So let's at least start going through it. So the first thing I would do is just write out everything explicitly. So we have our methane, and we have 2 waters. And then that gives us, so 4 hydrogens. You don't have to do this, but I like writing it out, at least initially, so you can really see what's going where. And then CO2. And so now just looking at it, you can start to identify what we need to break and what we need to make. So it looks like everything gets totally destroyed. So if we look, so just comparing, for example, carbon from our reactants to products, so we don't have any carbon-hydrogen bonds anymore. So it looks like we're going to have to break all 4 of those. And then looking, okay, water, we don't have any oxygen-hydrogen bonds, so we're going to have to break all 4 of these bonds as well. And now looking at our product side, so I'm going to make, though, a bunch of new HH bonds, so 4 HH bonds, and then form 2 CO double bonds. So does that at least make sense, kind of how to visualize it, how to go through it? And then from there, just some math and bookkeeping. So now I'll do bonds broken. So CH bond times 4. So CH lost again, so 414. So what do we get for 414 times 4? 1654. And then we have 4 OH bonds. So they're just single bonds. So that's 464, it looks like. Does someone have this number? 1856. Let's do our tally. So do we get 3510 for the total energy put in? 3,510. So that's kilojoules. And I'll put a big fat positive sign so we remember we're putting energy into the system. And so now let's look at the accounting for our energy gained for our bonds formed. So we formed 4 HH bonds. So does someone have 436 times 4? 1744. And then we had 2 CO bonds. And I said, don't forget to use the special number for CO. So 799. So what is that? 1598, right? And so let's tally what's our total that we got back. So it looks like 3342. And I put a big fat negative sign. And so right away I'm going to notice that this is going to be an endothermic reaction, but let's get the actual value. So negative 3,342 plus 3,510. So that leaves me with a delta heat of formation of positive 168 kilojoules. Is that what other people got? So 168. And so this is telling us, don't forget your kilojoules, so this would be an endothermic reaction. So that positive sign tells us we have to put energy in to make this transformation happen. So energy would be going in. This reaction might feel cold to us. Okay, that's probably a good stopping point. Yeah, let's just stop there. So let's stop here. Let's take a little 10-minute break, and so we can start our quiz at 2:20 and maybe get you out of here at least a few minutes early today. And I'm going to go ahead and stop the stream, and sometimes I forget to do that.